I'm Drago. I lead the research team at Waymo. Some of those folks are here, contributed to the work I will be presenting. Our mission, the research team, is to leverage machine learning and push state-of-the-art in autonomous systems using machine learning. And today, suitably with the team of the workshop, I will tell you some of our work on improving models of behavior, which is key for driving on the road. Okay, so Waymo is Alphabet's autonomous driving technology company, and we focus on two categories: moving people with our Waymo One service, and moving goods with our commercial delivery arm Waymo Via, which features these big Class 8 trucks and also some delivery vans. Since October 2020, with Waymo One, we offer the world's first fully autonomous service in Phoenix East Valley, 100% without safety drivers, fully autonomous. We call this rider only. And we started fully autonomous driving in San Francisco this year. And this is a video of our first ride there, which, if Zoom permits, you will see is already fairly complicated. There is this loading vehicle. There's people walking around on the street. There's double parked big truck. So we're progressing. This is just to give you an idea, and I don't know what is it, half hertz, but on the top you can see roughly. This is a viewer that shows pretty LiDAR clouds colored by the semantics of our perception system, which is all quite nice, and it's even nicer when you look smoothly. I think here, if you look long enough, you will see, for example, here we will execute an unprotected left turn, and we will be reasonably assertive. We won't wait for every single vehicle to pass. We will actually cut in at the right time and continue, which is great. And I think there is more scenes here. I think you guys get the idea, right? So that was just our very first ride. I think they get interesting from there. I think one thing, as much as I love our viewer, I think it's awesome. I went on a few self-driving rides myself, and when you're in the car, you see this. So there's something very visceral and cool watching the steering wheel turn and the car drive. And again, at half a hertz, I'm not sure if that's an experience to me, but I felt a big thrill in the beginning, and then it felt comfortable and maybe a little boring. So, keeps going for a while because we drive a lot these days. But it's a unique thing. I think we're in this, challenge for a reason. That's really exciting. And so, speaking of agents and behavior modeling, the city is full of highly interactive environments. This one we've shown before. This is crowds exiting the baseball stadium. So you can see tons of people exiting and going inside the vehicles. There's vehicles all around us also. And here we need to go through some fairly narrow passageway flanked by vehicles on all sides. This is in fully autonomous mode, by the way, on top. And we keep going. There is, I think, there's some people coming out of garages. But ultimately, if you look at this, right, we need to model and understand the behavior of these agents. And there's quite a lot of agents. If you come to this intersection, this baseball game really have a lot of people. There's hundreds of agents on the road next to us, right? And we need to process all of that and behaviors. Now, there's a lot of maneuvers and involved when we drive. Yeah, so here's a few other interesting scenarios. This one is just what you need to do to turn right on red. So it's unprotected red. There is all kinds of people around you. You can see vehicles, bikes, and when everybody clears, we will go. But this is we need to be able to do these maneuvers frequently and safely. Right, so here we go. We let everyone pass, including the, I think, motorcyclist. And you start getting interesting scenarios where you need to react quickly. Here, there's a bicyclist in our side of the road that just appears out of a collision instantly. And And so there's interactions with that as well. One other interesting part is, so we now also do autonomous driving to the public in downtown Phoenix. And downtown Phoenix turns out to be a place of a ton of construction. I did not realize, but they're really good. And this is us navigating makeshift construction area with need to interpret all these, poles and signs telling you where it's okay and it's not okay to go, right? And this is unrelated, strongly related to the initial road graph. So that is us doing this. What is next? Just latest news. We got driverless permit to take people around San Francisco. So more videos will be forthcoming. Fully driverless. We started driverless operations to Phoenix Sky Harbor Airport from downtown. And we announced Los Angeles is our next ride-hailing city. And here's even a clip of Los Angeles. It's again, dense urban area, actually quite similar to parts of San Francisco. And there is, again, lots of traffic. There is double parked vehicles that we need to pass and people loading and unloading. This is, I guess, par for the course that needs to be had. So hopefully with these videos, I gave you at least some intuition at 0.5 Hertz about the complex interactive scenes that we have to deal and handle. And I think this is a core part of what makes autonomous driving an interesting domain is the rich multi-agent setting. So we need to accurately understand and model behaviors of the road participants in order to make right decisions. So that's a difficult problem, but we have a key aid. So we have a huge trove of miles and observations collected by our own vehicles, millions of miles, where you can see how people actually behave in the wild. And we can use that data and learn models of behavior that we can then use, right? And so that's a theme in this talk. And I think around this theme, I'll present some of our recent work. So I will first talk about behavior prediction, also known as motion forecasting task. There we aim to model the behavior in a supervised or open loop setting for longer periods of time. We try to forecast the distribution of where agents may go. And then I'll talk about another part of our research on agent models, whose goal is to produce a robust closed loop. And let's talk about behavior prediction. What does it look like? So many systems in this space follow the structure, which we also described in an old paper of ours called multipath. You take in representation, the world state, representing the environment around you on the road. So this is the agents, locations, past history, the traffic light states, description of the road graph is a reconstruction with like the lanes and the road boundaries and potentially signs and so on, and their relationships. And then we feed this into a deep neural network encoder, whose job is then to decode a compact prediction of the future state of the scene. So if you have n agents in the scene, for each, we will produce k trajectory hypotheses. Those can go up to several seconds in the future with probabilities, with likelihood for each mode. And then with each trajectory is represented as a sequence of x, y, and maybe heading on fixed intervals with the associated uncertainty. And this is an example of these models in action. So this is a state-of-the-art model maybe from a year ago or so. And you can see there is predictions up to 8 seconds in the future. We show the top 6. The more saturated colors are the more confident, the more likely ones out of the set. I mean, these are ultimately agents are non-deterministic. You have multiple options for each. So when we initially started with multipath, we were actually computer vision people, and we used the raster representation to represent the scene, which is essentially an image-like representation. So you take all the features you have and you discretize them into some image grid, and then each channel is some other semantic property. And then you can apply your favorite computer vision architectures, which are good and powerful and so on. So we worked with this, but there is some drawbacks here. So there is an unpleasant field of view resolution quality trade-off. And so essentially, the finer you make the grid, the more expensive the compute. But the coarser you make the grid, then of course, the more you discretize the continuous entities that open perception can produce. So it's not great. And the other part that is very important for this domain, so long-range interactions are important. They occur, distances coming from afar affect you. If you apply a standard neural net architecture with 3x3 filters, typically how they're done, right? Then you need to stack quite a few layers until you have a neuron can see all the relevant signal that's needed to model long-range interactions. It's not great. So we move to a vector input. So these are polylines, ultimately representing most of the properties and associated also with continuous attributes. So who has polylines? I mean, you pass pose, you have a sequence of similar to app predictions locations. So that's a polyline. Lanes can be represented as polyline, their boundaries can be represented as polyline, sidewalks, and so on. And so now you can represent things arbitrarily accurately, but there is a cost, so you need to rethink the architecture. And so we settled on rethinking architectures for 1 year or two. And this is one that we published early this year. So maybe I'll say from last year, but this is essentially we ablated the space of options. And so essentially you can see the different types of input. For each, we ablated what is the best encoder for that type of input. So maybe agent poses are well consumed by LSTM, and maybe the road graph with something else. And then we carefully arrange how all these things are fused to produce the final embedding with some layer we call MCG, multi-cortex grating with this attention-like layer. So all of this, when it's all said and done, you get actually still a reasonably simple neural net architecture that's very performant, and at the end was state-of-the-art on the key data sets in this space, which is Waymo open motion dataset and Arguers. So we were very proud of this work. I think some people in this room contributed a lot to it and worked on it hard. It required a lot of domain expertise, and it has a lot of these custom details. And so it's difficult to trade off capacity versus performance in this architecture. It's too heterogeneous. It's not simple. You need also domain expertise. And so we wanted to rethink this space. And so we took a step back and said, okay, what are the goals of an architecture space for behavior prediction? And here's some desiderata that the team came up with. So first you want a simple architecture. Ideally, it should be easily usable by people that don't in any way represent experts in behavior modeling. Just general machine learning people should get home with this. It should be easily tunable. So you want to span with an architecture family, low latency and high quality, and you want to have knobs to tune and achieve the full operating spectrum. So you want that to be easy. And of course, you want highly scalable architectures with that. And so then a few consequences to this ensue. So one is, let's use transformer, right? Popular, I think by now, uncontroversial in many ways, right? Wildly popular in a ton of applications, and so should have great scaling properties here as well. And one of the interesting questions when you build an encoder is how to fuse modalities, and there are several approaches. So one of them is early fusion. So you just concatenate all the inputs, heterogeneous or not, and you apply cross-model attention on top. That's actually very uncommon. Most models at the time when we did this work had not done early fusion. A lot of models have done late fusion. So there, you just take each input and you apply attention just to the input itself and process it, and then you concatenate the embedding. So that's late fusion. And the team also explored hierarchical fusion, which is a combination of these two approaches. Next question is how to model the interactions in this transformer over the space, in the space-time lattice. So you have time and you have the scene elements over time. How do you attend to this? And here we built upon all the work. This was a collaboration with Google Brain called Scene Transformer. And ultimately, you can have several options. So you can have spatial attention, which is entities at the same time step. Obviously, they interact with each other. Temporal attention captures the dynamics of objects over time. And of course, you can have multi-axis attention, which attends to the full matrix. And so out of these, we made 3 different blocks that combine them in intuitive ways. So these 3 blocks were our units out of which we made the encoder, right? And that resulted in a paper called Waveformer, Motion Forecasting via Simple and Efficient Attention Networks, essentially exploring the space of choices that we outlined. And this paper is on arXiv, and it was actually submitted to CoRL and not accepted. And you know, I personally, it's presented at CoRL anyway. I like this paper. I think it's good. So here it is. Here's what the things you will find in the paper: a ton of interesting studies, learning about the effects of all these design choices. And I'll just show you graphs like this. I'll show you just one. For more, please refer to the paper. So this is latency, right? Slower models, faster models. This is quality, better models in quality, worse. And so you can see the kind of the curves here. It shows you that if you want low latency, so the green boxes are late fusion. If you want somewhat intermediate trade-offs between latency and quality, hierarchical fusion is good. And here, if I want the slower side, of course, and the early fusion is more expensive. But also what we're paying is state of the art. And this is actually with early fusion, which was quite uncommon in the architectures before. And furthermore, the state of the art is on both data sets. And this was obtained, which the team is proud of this, with a model that does not build in any special knowledge about the domain. So this is just a generic architecture. There was no knowledge built into it that's somehow special to all these inputs that come in. So that's pretty cool. We not only have this result, of course, we have the really good control over the full operating space and understanding how to build ourselves faster, cheaper models or slower and high quality. So yeah, this motion forecasting task is great, actually, as a workshop for architectures. And this is some results. I don't know if you can see again my favorite half-hertz video. Here's a bunch of pedestrians crossing. Here's the vehicles. Generally, the behavior is quite nice, following what you would expect in the graph. And here's another graph, somewhat unusual intersection topology with a bunch of U-turns that it's nailing. So ultimately, powerful model. And now let's talk about modeling interactions. So far, we're a bit more in architecture space. And so here is another simple scenario with what should be familiar to you, these colorful predictions. And now let's ask some questions. Even this simple thing looks a bit messy. So is this a predicted collision or not? Or maybe over there, is there a predicted collision? You can't see it with kappa hertz, but right, like what's the probability? These questions are very relevant when you build a plan, right? These are things you want. So would we say these agents interacted? Maybe. By how much? Right? And so let's dig a bit into the output of this network. So far, and a lot of the traditional benchmarks in the space treat predictions as independent. So you say every agent, given the scene, there's a set of what I would call marginal predictions, right? So independently, these are the outcomes for this agent. And so they're good by themselves, but they can well represent interactions. Here's an example: agent A and B each can turn with 50% left or right. So with 25% right, they will hit each other. And you have no way to represent in this this output the case that maybe that should be unlikely. Maybe that doesn't happen in the data and should be 0. And so that's not very good for planning. Ultimately, you want to see interactions of yourself and other agents. If you just get marginal predictions, it's limiting. So the other extreme is joint feature prediction, right? So you say, oh, I'm just going to have the full probability table over all agents, right? So it's exponentially big, but now I can represent everything because I have a separate entry for every possible, say, for two agents, every possible outcome for the pair, which is great. I can represent maybe there's no collision there. Now the issue is what happens when the agents blow up. Actually, this output was adopted by Sync Transformer. They just handled it in a particular way. They said, okay, you have 6 futures total for the whole world, no matter how many agents. That's very limiting. I mean, you have 100 agents. If you just say 6 joint futures, that's not great. Now, how do we treat this space in a more principled way? So here comes another paper, joint future prediction, at this conference. Please check it out later. I think it will be in a poster. This is a deep network that does pairwise graphical models CoRL head. And so it captures factor joint interaction between multiple agents. So let's say here's the agents in the scene. We're going to impose an interaction graph on them. So in this case, just maybe 4 agents and a fully connected graph as an example. Then given this, we first would predict a set of marginal trajectories for every agent. These are roughly generally the outputs you expect for each agent. But this doesn't capture yet the interactions. And so then given the graph, you also form pairwise potentials. And the pairwise potentials capture the pairwise table of interactions between these marginal predictions. So essentially now you can start maximizing the likelihood. You can start to maximize the likelihood over the whole joint representation. And you can backprop it through this model and through the network and learn yourself both the features and the properties of the head predictor layers that model the joint distribution represented in this way. And so that's quite powerful because you can now actually what you can do is now the question is what is the graph? You can shift between sparse and dense graphs and study what happens. So you can have no graph, that's just the marginals, no pairwise relations. You can have the fully connected graph, which is all pairs of agents interacting. And then you can need to do loopy belief propagation. It's approximate if you want to do inference in that model, right? And then you have in between options like star graph, which has exact inference, and you can backprop through that easily. And typically, when you do a star graph, you want to center it on the AV because we have an AV-centric objective. We want to drive relative to all the others. We want to model our relationships with the others. So if you have to pick something, that's very natural. And then we have a dynamic graph too, which is it's incremental construction within the model. So if you predict the marginals for every agent, you can check what marginals overlap with others. And if marginals overlap in spacetime, they could be interacting, and then you can have a pairwise potential. So you can have a dynamic interaction graph as well. And so, of course, you can see here, this is the most expensive, and these also start becoming more approximate inference, more dependent on number of agents in the scene and so on. And here it's, of course, goes all the way to no interactions. So let's see, will this move? I'm clicking things. Okay, let's see. There we go. And so before we go ahead more, let's talk briefly about the metrics. So there is this metric called minimum average displacement error. Essentially, it's a metric adapted for multiple outcomes for an agent. So if the agent is stochastic, you give it a budget of, say, 3 or 6 guesses, and then you check how far is the nearest guess. So that's one fairly permissive way to still capture multimodality in the metric. And here we will show some result with a metric called joint NAD, where you essentially take the minimum outside and you say for some set of interactive agents, in our case, typically 2, otherwise things also blow up. You just take pairs of their futures and you check out of K guesses for the pairs, what's the pair that's closest. So you can't cheat there, you need to match both at the same time. And what happens? So in this joint NAD metric, you can see that these intermediate graphs, especially the star AV-centered star graph or the dynamic graph, do significantly better in pairwise prediction. This is actually our interaction challenge. We launched it specifically to push people to move beyond just marginal predictions. So check it out if you want, but it's a good way to measure how well we model interactions. And what's interesting is actually fully connected does pretty bad. And that can be many explanations, but it's tied to too many pairwise potentials, approximate inference that may or may not converge in all cases well. So there's a happy medium there that's significantly better than the default, which is the great part. And here is another metric, which is predicted overlap with the autonomous vehicle. So this is how often you have some agent overlapping your path. And of course, the scenes we have, no one hit you, so this should be 0 in theory. So lower is better. And these two models, again, do significantly better than the default, which is just marginal predictions, which is great. And last but not least, we beat the state of the art in our own interaction challenge with this work, which is not a bad thing. This is the JFP work, and it compares to Sim Transformer, which is a past work. And we had a challenge, some challenge winners from a couple of years ago. So, so that's what I wanted to say about behavior prediction models. Now, let's move to agents. And I'll start with simulated agents. I think it's a bit easier to tie in the story. So, simulation is an essential tool for testing how a driver handles complex scenarios, ones that you may not even want to put on the road. Also, simulation is key for validating releases in a consistent way because you can keep replaying the same scenarios. But utility of the simulator depends largely how realistic it is. So that's why we're working on building the most experienced simulator, if we can. And try we do. Now, when you think of simulator realism, a key challenge is modeling the other road users. It's not only about sensor realism, it's actually the fidelity of behaviors is highly important. And I'll show you my favorite example. If you've seen talks of mine, you've seen this before. So you have, only maybe not at this frame, right? So you have the cyan agent, which is the position of our driver in simulation. Green was the position of the agent when it collected this scenario. And you have this obnoxious purple agent that plows straight into us because when the scenario was collected, that of course was empty space. And so we were not there, now we're there in simulation. You cannot just replay the logs and hope the outcomes are realistic. You can get with highly unrealistic collisions. Of course, those are not helpful whatsoever. And so to do better, you need agents that react realistically. And this requires closed loop control policies, which we can learn from demonstration real world data. And so to this end, we published a work this year called Symphony, Learning Realistic and Diverse Agent for Autonomous Driving Simulation. And at the core of this Symphony work, it's an imitation learning approach for agents. So at its core, it has a standard learning from demonstration algorithm. It could be behavior cloning or NGAL, but we augment it with two additions. One of them is parallel beam search, which refines the policies on the fly by pruning states that look unrealistic based for the agents using a trained discriminator. And second, we also add a hierarchical policy model, which helps produce diverse outcomes. And I'll show this just in a couple of slides in more detail. So how does this parallel beam search work? So you start at the time when the agents when you start applying a rolling policy out for the agents. So you generate an action for all agents by some policy that you learned with BC or NGAL. And then you can prune branches with higher scores of unrealism based on a discriminator. And then as you prune some, you can resample others, maintaining a certain set of diverse outcomes. And then you roll this out for as long as you want to play your scenarios. Right? And this, of course, helps. So if you do this, your collision rate and off-road time you go off-road decreases significantly compared to the baseline. But actually, it hurts diversity of the outcomes. And we introduced this metric called curvature Jensen-Shannon divergence that captures that. So what is this curvature Jensen-Shannon divergence? Essentially, you look at this data set of log behavior in blue and agent behaviors reproduced by a policy. And you see how often you drove straight mostly or right, left at various angles. And so it makes a histogram of these arcs and their shapes. It turns out that, say in this case, the agent preferred driving straight a lot more, but is undersampling right turns and left turns. So how do we recover the diversity? And that's where hierarchy comes in. So we have two models. So first, there's a goal generating policy. At the moment you want to let the agents go, you produce essentially a route for every agent given a model, and that route is self-fixed. And the route is essentially a collection of route graph segments. So it's some geometry that you want to follow long term. Then conditioning on this route, the policy executes the steps trying to follow the route and of course maintain realism and so on. And so what that happens to do is it helps with the diversity because you can sample routes realistically matching the true distribution. And it does happen to fix the curvature JSD. So now you get basically the best of both worlds when you combine these two additions to the pure imitation learning approach. And here's some examples. So in red is like the baseline agent without research and hierarchy. And this is probably, I think it's behavior cloned agents in red. And they just both plow ahead into each other, while in the other case, the agent on the top yields until the relevant other agents cross the intersection and only resume. Here is another example. So again, the red agent is the baseline non-symphony agent, and it goes in some wild sojourn plowing into vehicles. But in symphony, again, the interaction is realistic, and one of the agents waits for the other to pass. Let's move on to planning agents. So this is a work from Iros, and it essentially follows up on the previous work. So this is essentially us exploring how far can you go with an imitative agent for planning. And so the idea is exactly like the agent I showed you, the hierarchical MGL agent. So you pick a route, and then you condition on this route, and you train an MGL policy for the agent, right, in closed loop. And that ultimately is applied for the duration of the rollout, right? This MGL policy, ultimately, our model, the conditional part of the model is trained with two losses. One is behavior cloning, and one is the MGL loss, which is closed loop loss. You're rolling out futures and scoring them with the discriminator and back propagating through the motion model, which is differentiable to learn behaviors robust to closed loop. And so theory predicts that adding this MGL loss will yield benefits. And we affirm this now in practice experimentally, right? But first I'll show you an example. So this is planning agent trained with behavior cloning. So you still have a route and you condition on it, but then you train just predictions to the close every step. And so you get stuck in this narrow example and we cannot proceed. In contrast, our agent that combines MGL and BC losses successfully proceeds through this fairly complex narrow area and continues on its way. So we evaluate these policies with logged agents and conditioning on the expert followed route. So whatever the expert followed in the demonstration, we condition on that and see how well they'll execute this. And we measure here the policy success rate. So success rate is if you didn't collide and you did not go off-road ultimately in these scenarios. And you can see that our best policy that combines MGL and behavior cloning significantly dominates behavior cloning and slightly dominates MGL. However, I mean, there's a bit of an issue evaluating this policy on the same goals achieved by the expert. This could be overly optimistic performance estimate because there could be spurious correlations you're not discovering. Ultimately, you're giving a lot of hints based on the route and following exactly the log behavior of agents. This, for example, cannot tell you, can it follow on if I gave it another route? Could it follow it or not? Okay. So that's exactly what we started testing. It says here is we're testing it with a route crossing passing across the intersection while the expert policy turned on the right. So this is one example. And of course, when you do these things, you also want to turn on interactive agents. So now we're testing on novel routes with interactive agents. And you can see here, the gap is significantly bigger, right? So it shows that this BC plus ALGL combination has significantly better generalization ability. And that there is still some gap between novel routes and the expert route a little bit still. But overall, yields quite well-performing agents. We also continued to study some of our model further, which led to a paper in this conference. So this is a short spotlight. I encourage you to go attend it in December 18th and learn more from the direct author, Ellie. Essentially, the question we asked ourselves is, okay, so how do these models perform at the range of examples? Easy, medium, or very hard, right? How do these policies compare on those? Well, where do you get these labels for the examples? Well, you could just label them manually, but what we also did is on separate data, we trained the classifier, and this classifier is trained so that data contains undesirable outcomes where, say, the expert resulted in close to collision and or close to off-roading. And so we trained to classify those. And so we produced this classifier, and now given this classifier, how can you use it effectively? It essentially tells you what are the difficult examples, the ones that are likely to not succeed. And turns out in this paper that just with 10% of the examples and the appropriate, using the classifier outcomes appropriately, we can significantly improve the performance of the model. So you can move from, even with 10% of that, you can move from a baseline of over 3% and a quarter failure rate to below 3. And you can also furthermore do it across all, you can beat the baseline across all the bins of difficulty with certain schedules that we pick. So to learn more, please refer to the spotlight. I will talk one last thing, which is work from NeurIP's autonomous driving workshop we presented a couple of weeks ago, which explores the relationships between imitation learning and reinforcement learning. And so this method is built on the intuition of this work. It explores the intuition that imitation and reinforcement learning offer complementary strengths, where, imitation increases realism and ultimately removes the need for complex reward design. But reinforcement learning can improve robustness, especially in the more data-low regimes, right? Because there will be fewer examples there to imitate. And so in this approach, we combine the benefits of both imitation and reinforcement learning by crafting a loss that combines them. Right? And so how does this work? On examples in distribution, we apply two losses, reinforcement learning loss and imitation loss. And on examples out of distribution, we apply reinforcement learning, like 30 word loss. And ultimately, the way this is implemented, we call this simple method VC-SAC. And it's a modification of soft critic where we add an imitation term for the examples that are in distribution. And reward function is kept very simple. It's just there is a penalty for collision and off-road in the outcomes. And so what happens? I think you can see here, this is again results, this is familiar from the spotlight. These are examples ordered by difficulty. This is the most difficult ones. And you can have, this is SAC is in orange here. And you can see that it, on the more difficult spectrum of examples, it's more robust than the MDL agent, which we just talked about. It's purely imitative of behavior cloning. And those particularly tend to do bad with the top 1% of difficult examples. And BCSAC is stronger there. Now to dive in slightly more into the results. So when we train with all the training data, you can see that in this is evaluating top 1% hardest, top 10% hardest, top 50% hardest. BCSAC typically has a lower failure rate. Yeah. But MGL beats it when you take into account the bottom 50% easiest examples still, because there we have a lot more examples as classified as difficult model. And if you take just the top 1% difficult examples and train the model, this is essentially the low data regime where you have a lot less training data. Now, the imitation term, of course, becomes a lot less effective. At this point in the low data regime, reinforcement learning looks a lot more desirable. Now it's better across all ranges, but that wasn't exactly true as the data sets go. And so maybe a little bit of intuition here. So that is MGale. Comes quite close to a vehicle where a pedestrian just exits, which is not optimal. And here, BCSAC provides additional clearance around. By the way, some of this robustness, just want to point out, comes at the cost of progress. So it may be more robust, but the progress is significantly less. Right? And there is even on top some cost of progress. And you can see some of this. It learns to be more cautious and drives around some of the more problematic cases, as opposed to staying in lane here. And there is a vehicle sticking out and it tries to brake, almost succeeds, but not quite. That's MGale. And here it's early on mitigates it by changing lanes to the right. And so there's still a lot of interesting things to explore at the intersection of imitation learning and reinforcement learning. You guys may be familiar with the Waymo Open data set. We have provided at least some data for imitation learning. That's 100,000 scenarios of interactive examples that we released. And so, and of course, this data set has a bunch of other things. We keep improving it and evolving it. Please check in occasionally to see what else we put in, but I think it enables research of the kind I just showed and more. And so that was my talk. Thank you very much for attending. And if you want to see a lot more of our papers, first, we have 4 papers at this CoRL, so please check them out. Second, at waymo.com research is a lot more of our papers. About things that we have explored that I did not have time to present today. Please encourage you to check it out. Thank you.